Hello and welcome. I'm Ray Wood from Hellma UK, and today we are going to look at the performance qualification of UV-Vis spectrometers, both in general usage as well as where compliance to the European Pharmacopoeia is required. First of all, we'll review the key parameters that define the performance of a UV-Vis spectrometer. And then we'll look at what might need checking and when. We'll look at what filters are needed to carry out these tests and at the principles of testing. Then we'll review some guidance on filter selection. Finally, we'll explore how the data collected during validation can help support other key decisions. And we'll close with a review of the help and resources available. Unlike many laboratory and process instruments, spectrometers require little pre-calibration before use. Most of their settings are fixed in manufacture, and typically all that is needed is a blank to take out any baseline offset. But time, usage, operating conditions and accidental damage can degrade these fixed settings and will impact on the spectrometer's performance and the accuracy of your results. If any of those preset calibrations have changed, you may be reporting inaccurate results, and you'll be unable to support them with any evidence of the reliability of your measurements. So validating your spectrometer against traceable standards is the best way to have confidence in your results, and is important for meeting the latest regulatory requirements. There have always been 4 key parameters that define the performance of a UV-Vis spectrometer: absorbance accuracy, wavelength accuracy, stray light levels, and optical resolution. While the latest edition of the European Pharmacopoeia, EP10, has added a test for photometric linearity to these 4. We'll now look at these parameters in a little more detail. First, let's review absorbance measurements. Whatever the optical arrangement of your spectrophotometer, the detector can only measure the light transmitted through the sample, not the light absorbed by it. Of course, calibrated against a suitable blank, it can calculate the absorbance. But we must never forget that absorbance has a logarithmic relationship to the transmittance that we actually measure. Modern instruments can handle this very easily, but they hide the scale compression that was once routinely seen on analogue displays. Look at the bottom scale. You can see very good resolution to around 0.5, but it gets worse as you go further up, and after 1.5 it becomes effectively unreadable. Because of this and the tiny signals being measured at these higher absorbance levels, the latest version of the European Pharmacopoeia requires measurements above 2 absorbance to be subject to a risk assessment. Most UV-Vis spectrophotometers work over a wavelength range from 190 up to 800 or 1100 nanometers. Traditional monochromator instruments may have dual or single light sources and will have some critical wavelengths where lamps are switched over or blocking filters moved into the light path. You may hear this happening during a wavelength scan. Modern instruments with CCD array detectors will have fewer moving parts, but in all the different designs, any mechanical movement will lead to wear, while external shock and vibration may cause internal movement or distortion, and ambient or self-generated temperature changes will cause expansion and contraction, all combining to change the delicately aligned optical assemblies. So regular checking of wavelength accuracy is a must. Stray light is defined as any light that reaches the detector but does not pass through the sample. This can be caused by optical misalignment as well as internal reflections or scatter from items inside the sample chamber. So take extra care when fitting any alternative sampling devices. Stray light can also be the result of poor sealing around the sample compartment. The effect of stray light on absorbance accuracy is much greater at high absorbance values, as can be seen on the graph. So this further supports the European Pharmacopoeia in their requirements for a risk assessment when measuring absorbance levels above 2. Regardless of the type or optical arrangement of your spectrophotometer, there will, by definition, be a dispersion device somewhere. This will break down the light from the source or the sample into its component wavelengths. The optical resolution will primarily be defined by the quality and condition of this device, along with the slit that selects the range of wavelengths allowed to pass through the sample. Together, these set the spectral bandwidth, or SBW, of the instrument, which enables clearer separation of closely grouped peaks. Some spectrophotometers will have variable slit widths, which effectively change the spectral bandwidth of the spectrophotometer. Checking optical resolution on these instruments becomes more important to ensure the setting is correct and that no wear or movement has occurred in the associated mechanics. Photometric linearity is a new test introduced in the latest European Pharmacopoeia. For compliance, this involves checking at least 3 absorbance levels and plotting the linearity between them. This is a good and practical check of system performance. How often these tests should be performed is a difficult question to answer. It should certainly be done more often than once in a blue moon. Routinely checking these 5 parameters will enable you to verify the performance of your spectrometer and give you confidence in the results you are reporting. But routinely checking will mean different things in different circumstances and will depend very much on your usage of the instrument, its working environment, and especially whether it is shared or dedicated. These checks could be done on a simple timed basis, monthly, weekly, or daily, but in some instances it may work better to do it in line with its use. For instance, at the start of each new batch, or at the changeover of each shift, or when switching to a different type of analysis. So this frequency needs to be defined for each spectrometer, and this is best done as part of your quality management system, where it can be fully justified and detailed for all the work being undertaken on it. The latest European Pharmacopoeia gives some guidance on which parameters should be checked depending on the type of measurements that are being carried out. If you are making an absorbance measurement, a concentration measurement, or a kinetic measurement, and whether this is being done at 1 or more wavelengths, then the spectrometer should be tested for wavelength accuracy, absorbance accuracy, stray light, and photometric linearity, while optical resolution should also be tested if you are following a specific monograph in the Pharmacopoeia that specifies this test. Where just the wavelength of an absorbance peak or valley is being identified, wavelength accuracy and stray light should be tested. Where the wavelength and absorbance level of an absorbance peak or valley is being measured, Then the wavelength accuracy, absorbance accuracy and stray light should be tested. Where the spectrum of a wavelength scan is being compared to a reference scan taken on the same instrument under the same conditions, then the absorbance accuracy and the wavelength accuracy should be tested. Of course, once you are familiar with all the tests, it may be just as easy to do them all regardless. To test these different parameters, a wide range of materials are available in the form of optical filters. These filters can be tested on reference spectrometers and given certified values that enable full traceability to NIST standards. So along with their relevant certificates, we refer to these filters as Certified Reference Material, or CRM. The two main types of filter are glass and liquid. Glass, where various substances are fused into a glass substrate that is cut and polished, then mounted in a frame that can be inserted in a standard spectrometer cuvette holder. And liquid filters, where chemicals are dissolved in a range of solvents and sealed in a standard 10mm cuvette. These can be put together as sets to enable a specific parameter to be fully checked, or to check a range of parameters to meet regulatory requirements. Historically, spectrometer validation has been carried out to confirm the instrument's performance against its published specification. This also enabled a standardized set of filters to be supplied to validate all spectrometers with specifications capable of meeting the European Pharmacopoeia performance requirements, a so-called EP filter set. In the latest version of the European Pharmacopoeia, this testing to specification has been replaced with testing for fitness of purpose, or suitability for the application. This means that the performance of the spectrometer has to be validated against the requirements of every application carried out on it. So no single filter set will meet all requirements. Personalised filter sets suitable for all your regulated applications will be needed, and it will become impossible to add an application for which the spectrometer has not been checked as fit for purpose. Good laboratory practice would indicate that checking the spectrometer at levels that bracket the range it is intended to be used over will be the minimum requirement to prove suitability for purpose. And this is also the guidance given in the latest European Pharmacopoeia, EP10. Validating the absorbance accuracy of your spectrometer can be carried out with a number of different certified reference materials. The following are all recognised as suitable within the European Pharmacopoeia. Neutral density, also called ND or grey glass filters, have a relatively flat absorbance over a wavelength range in the visible region from 400 to 800 nanometers, and are available in values from 0.04 to 3 absorbance. Potassium dichromate liquid filters are a long-established spectrometer reference material, and at different concentrations can give absorbance levels from 0.1 to 3 at wavelengths of 235, 257, 313 and 350 nanometers in the UV region. And finally, there is niacin or nicotinic acid liquid filters that at different concentrations have absorbance levels from 0.25 to 1, measured at 213 and 261 nanometers, deeper in the UV range, making them very useful for validating spectrometers used in specific life science applications. So the challenge for EP10 compliance is to find a combination of filters that bracket your expected absorbance range and fall within your operating wavelength range too. If you need any help finding the best combination for your application, simply contact your local Hellma office. Validating photometric linearity can be linked with and even performed at the same time as testing the absorbance accuracy. Simply select one or two additional absorbance filters with values between your limits and at the same wavelengths as your other absorbance filters. Measure and record all results, then plot the measured values against the certified values and check this is a straight line. To comply with EP10, this needs to have an R-squared value of not less than 0.999. To help you with plotting and calculating this value, you can download a simple tool from our website. We'll just have a look at that here. You can see quite simply you enter the type of filter that you're using here, the serial number of that filter, the absorbance value from the certificate, and then the values you've measured. It automatically plots the line for you and then calculates the R-squared value here. Very, very simple and quick way of getting to your R-squared value. Wavelength validation can be carried out against glass and liquid filters. Glass filters can be made from holmium oxide, which has wavelength peaks at 279, 361, 453, 536 and 638 nanometers, covering the upper part of the UV and some of the visible spectrum. Another type of glass filter is the didymium filter, which has standard wavelength peaks at 329, 472, 512, 681 and 875 nanometers, covering mainly the visible spectrum. The holmium liquid filter has wavelength peaks at 241, 287, 361, 536 and 640 nanometers as standard, going a little lower into the UV spectrum, and has several more optional peaks depending on your requirements. The didymium liquid filter has wavelength peaks at 329, 469, 575, 740 and 864 nanometers as standard, and up to 8 others depending on the optical resolution required. The HODI filter is a mixture of the holmium and didymium liquids that offers up to 22 different wavelength peaks from 241 up to 864 nanometers. The rare earth liquid filter is ideal for wavelength validation in the low UV and is especially suitable for life science applications. It has wavelength peaks at 201, 211, 222, 239 and 252 nanometers. So the challenge for EP10 compliance is to find a filter with wavelength peaks that bracket your wavelength range. And this may require 2 different filters if that is a very broad range of wavelengths. Or maybe it will involve selecting a filter with peaks close enough together if you are working over a very narrow wavelength range. If you need any help finding the best combination for your application, simply contact your local Hellma office. Stray light can be checked by inserting a filter that absorbs all the light below a certain wavelength, known as a cut-off filter. These can be glass but are more commonly liquid filters made from various solutions. Potassium chloride has a cut-off at 200 nanometers, sodium iodide at 260 nanometers. Acetone has a cut-off at 325 nanometers and sodium nitrite at 370 nanometers. EP10 calls for measurement to be made at a suitable wavelength for your application and against the blank solution used in producing the filter. Optical resolution is checked by measuring the peak to valley ratio of a solution of toluene in hexane against a hexane blank. By comparing the peak at 269 nanometers to the valley at 267 nanometers, the ratio can be converted to a spectral bandwidth between 0.25 and 4 nanometers. If you are validating an instrument that has different applications requiring the use of variable slit widths, then the resolution should be checked for each setting that is used. Whenever you validate the performance of your spectrometer, you are gathering valuable data on its condition. Logging and storing this data is a great resource for use in setting service and maintenance schedules, as well as one of the important inputs to your quality management system in justifying the frequency of routine validation procedures. Hellma have created a number of record cards that can be used for gathering this data and are available for download from our website. We can see some here. They're used by simply inputting your wavelengths of validation from your certificate. That data is transferred to here where the uncertainty from the certificate is also added, and you can add the uncertainty from the specification of your spectrometer. Those values are then turned into higher limits and lower limits, which we use for tracking out of limits results. As we do the validation over time, results are stored here, and when an out of limits reading is taken, it is highlighted in red. That data can be stored as a trend, and we can see that here, the trend of those results going on over time. And we can see the result that was out of limits here above the red upper limit line. We can do exactly the same thing for absorbance measurements. The absorbance measurements from the different filters are here. We take the uncertainty from the certificate and from the spectrophotometer that you're using to create the upper and lower limits here. As we're doing the validation over time, if we do see a result out of specification, it's highlighted in red. And again, we can see that on the trend, we can see the trend going along there, and we can see the result that was out of spec below the red lower limit line. Our CRM brochure doesn't only contain the products we've been talking about today, but also includes usage guidelines, as well as simple procedures. It also includes QR code links to online video tutorials and pointers to regulatory requirements too. Our website, www.hellma.com, has many pages of information on certified reference material, and from here you can also download the brochure, the photometric linearity tool, and all the control cards as well. You can get updates on our latest news by following us on LinkedIn. Use these connections or find the LinkedIn button in the footer of our webpage. Hellma have many offices around the world where local support is available to you. Contact them directly for the fastest response to your questions and inquiries. Let us help you find the best solution to your requirements. Thank you for taking the time to view this presentation. We hope it has helped you, but if you have any questions or would like more information, please let us know.